Hi, I'm Leon Starr, and welcome to my course on how to specify software in complex safety-critical systems. This is the second in a series of short videos that I will be uploading to YouTube throughout 2024. Here we have part 2, which completes our introduction and picks up from the exciting cliffhanger at the end of part 1. If you haven't seen part 1, I recommend stopping now and doing that first. In part 1, I described the limitations of the default box-in-box approach to managing levels of detail and complexity in a software system specification. As promised, here in part 2, we're going to look at a powerful alternative. This alternative is actually a combination of 3 ideas, which are separation of concerns, execution semantics, and platform independence. Ooh, I know these names aren't exciting you right now, but hear me out. Used separately, these techniques are of limited value, but in combination, they will keep you from over or under specifying and maintain a consistent level of detail throughout your software system. This means that you will know when a model is truly detailed enough to be called complete, and you will know whether or not you have gone too far and started biasing the developers to an arbitrary design. And you'll be as confident as you can be that you haven't missed any non-design details or tricky edge cases. Now, I don't promise perfection. I don't claim to build perfect models. What you'll get, though, is substantially increased confidence all around and quality for the time you spend focused on the problem. Let's dive into each idea separately, and then we'll see what happens as they are combined. Let's start with how we handle the separation of concerns. Any complex system requires expertise in a variety of distinct subject matters. The corresponding subject matter experts each have their own unique view of the system and their own specialized vocabulary and deep knowledge of behavior relationships and relevant computations. Reconciling these diverse views into a coherent system specification with a minimal set of required dependencies is a serious challenge. Fortunately, our modeling approach is designed specifically for this task. The modeling concept we use to represent each separated concern or subject matter is called a domain. There are a variety of notations you could use to represent a domain symbol, but here I'm just going to use a simple oval. Now the names here are a bit whimsical, but I want to emphasize that we're not modeling high-level functions or processes so much as bodies of knowledge. Instead, it is best to think of each oval as representing a distinct set of semantics, which is just a fancy word for vocabulary. And here we're imagining the subject matter experts talking to one another using their own modeled terminology. You can also think of domain vocabularies as non-overlapping ontologies. In fact, one of our partitioning tests is to ensure that the same word with the same meaning doesn't appear in more than one domain. This is all getting a bit too abstract, so let's get to a concrete example. I'm going to use my elevator case study for teaching purposes, along with others throughout this course. I chose elevators since you all probably have personal experience with them, so I don't need to waste time explaining how they work, and we can focus on the specification and modeling. Now, this is not one of those trivial elevator system examples you may have seen before. This case study is intended to support skyscrapers providing express service with the ability to lock out certain floors. You can read more about it on my GitHub site if you like. Here I'm just going to talk about how we factor out the domains necessary to define such a system. We start by identifying that one domain that establishes the business purpose or primary application of our system. It tells us what the system is supposed to do for the primary stakeholders. Consequently, it's going to drive the requirements for any supporting domains. So we want to define that primary domain as early as possible. The business purpose of our elevator system example is safe and efficient vertical delivery of people and goods inside a building. Let's call this domain elevator management. Next, we need to figure out the vocabulary required to describe this particular subject matter. We're looking for terms that make an elevator system, and ignoring any terms generic to a variety of systems. So, sticking to elevator specifics, we can specify cabins that travel inside vertical shafts. We can define banks that organize a group of shafts servicing the same floors and operating with the same speeds and door management protocols. And we have shaft levels that define the destinations available to a given cabin. We dispatch a cabin by defining a transfer and service direction to a given shaft level. Not only are we defining a vocabulary specific to our system's primary purpose, we're providing the semantic building blocks we need to define our elevator service policies and safety protocols. We exclude terms like motor, sensor, button, and so forth. These terms are not specific to any elevator system since they can be configured for a wide variety of applications. You might be thinking, yeah, but if you leave all that stuff out, this domain's not going to be that complicated. Yes, that is exactly the point. We'll be able to put the spotlight on safe, efficient transport policies without getting distracted by tons of other details. And this, in turn, will increase the transparency of our modeling decisions so that our subject matter experts and stakeholders can check our work and point out all the nuanced cases we might be overlooking. It's not that those other details aren't important. In fact, it's precisely because they are so important that we want to focus on them without distraction in their own domains as well. We'll get to these in a moment, but let's see how elevator management is in fact a source of requirements for these other domains. Imagine using the elevator management domains vocabulary to describe some example behavior. Let's say we want the cabin in shaft 1 to go from floor 5 to the lobby shaft level. A transfer to this destination is created and managed until the cabin reaches its shaft level destination. But the transfer itself is somewhat opaque from our perspective. So we implicitly place a requirement on some domain that actually understands how to initiate and control motion during the transfer. What domain could that be? Kinematics seems like the relevant subject matter for the job. The name seems a bit grandiose for our purposes, though, so we'll just call it the transport domain. The transport domain doesn't need to know anything about elevators, but it does know all about moving a physical mass along an axis at the proper acceleration. Our vocabulary here is physics-oriented with terms such as axis, stop, acceleration ramp, motor, and so forth. Transport has no idea what a door or cabin is, as these are just special cases of a physical load. Cabins go up and down, doors move horizontally. This domain can compute a set of speed or braking commands for a motor using feedback like current position, current speed, maybe motor status like whether or not it's overheating or non-functional. But how do we actually interact with the motor? Signal-based communication is yet another subject matter that has nothing to do with physics. The expression of a motor command or the need for up-to-date sensor data implicitly defines a requirement for device interaction. Signal I/O is the subject matter concerned with digital and analog communication. It gathers raw data and transforms it into meaningful values. It doesn't know what the values mean. It just knows how to condition the data properly using the appropriate parameters and scaling. Similarly, it takes meaningful values or commands as input and generates the appropriate raw device-specific values. Signal I/O uses terminology like input point, conversion group, cooked value, sensor, actuator, and so forth. It has no idea what a motor is. If you want to see more detail on this whole Signal I/O domain, get your hands on the book Models to Code, which I wrote with my colleagues Andrew Mangonia and Stephen Meller. Since its publication, a lot more progress has been made in this area, so get in touch if you want to see the latest. Similarly, we factored out the UX, user interface, since, well, buttons and lights, while useful in our system, are certainly not specific to elevator management. We will need a way to specify precisely how all these domains are connected to define a complete software system. We've already seen the example where a statement about behavior originating in the elevator management domain leads us to a requirement satisfied by the transport domain. It turns out you can just look at the vocabulary in each subject matter to see the obvious source and destination of requirements. I like to think of it as the flow of requirements from one domain or subject matter to another. Or you might prefer to think in terms of dependencies, which is also fine. I think this is really amazing. You can organize your details not by obsessing on the functions, algorithms, or behaviors, but simply by understanding the relationship from one body of knowledge to another. Everything else flows from that. Note that the vocabulary of a domain can provide solutions to more than one requirement source. Signal I/O can specify interaction with buttons, lights, and motors, since it doesn't know what any of these are anyway. So where do we stop defining domains? Well, we keep going until all the requirements are covered to satisfy our desired system behavior. We won't necessarily model all of these domains, but you probably always want to model at least the primary application domain, elevator management in our case. Unlike the boxes in boxes approach, there's no notion of high versus low level of detail. Each subject matter is modeled at the same level of detail. They're just different details. You might note that some domains are closer to the primary application, while others define more general purpose terminology. This still doesn't answer the question of how we establish a consistent bottom level of detail or lowest degree of semantic granularity within each domain. One of the great failings of modeling has been the inability to confidently and consistently show that you've provided enough detail to actually be done modeling. And that's where our next important idea, execution semantics, comes into play. If you take the approach of boxes in boxes with its spectrum of high versus low level detail, you'll never define a bottom level of detail good enough for the specification. You'll just get a vague point where concept turns into code. And in that gap, a lot of difficult problems that could in fact be sorted out across all platforms independent of any particular coding solution would be left for the developers to figure out. So we need to provide a set of primitives for that bottom level that can be translated or mapped to any particular implementation. We call this set of primitives execution semantics, and they define the data, synchronization, and actions necessary to unambiguously specify what the code must do without specifying how it is implemented. I like to think of these execution semantics as a set of Lego-like building blocks. No matter what subject matter you are describing, the bottom-level details are a combination of these blocks. They define a lowest-level logical foundation for specifying any domain. And we have a set of rules for executing these semantics, so once rendered in the building blocks, we can run the models. We can generate code from them, or we can create a variety of artifacts, domain-specific languages, ontologies, simulation and validation elements, and so forth, depending on your project's needs. As I pointed out in part 1 of this introduction, you can't do this with natural language alone. This course is largely dedicated to explaining these blocks and how you can put them together to specify the concepts and rules of the domains you choose to model. There is no lower level of detail required in the specification beyond these execution semantics. Consequently, each modeled domain is equally detailed. It's just that the subject matter, the arrangement of these executable building blocks, is different in each domain. Resolution of our model elements into execution semantics gives us two benefits. First, we know exactly how deep our details need to be in any given subject matter to make the model executable. And second, we're in a position to run our models and ensure that our specification is internally consistent. We can also rely on model execution to support traceability and automate system validation. That's two concepts down, and now on to the third, platform independence. One of the big areas where software models get bogged down and fail is when it comes to the target platform. This platform is always changing, and if the models are tied to it, they will have to keep changing with it. We'll never keep up with the platform, and our models will be castles of sand constantly being blown over. On top of that, any given platform brings with it tons of extra details, changing the language of our specification so that we have to over or under specify to keep up. Our challenge then is to free ourselves from any specific platform, while at the same time ensuring we have executable detail. If we can specify our models on a stable, platform-independent foundation, we can work productively, keep them up to date, and not have to keep backfilling. By platform independence, we mean the same specification can be implemented on a wide variety of platforms, programming languages, operating systems, concurrency mechanisms, and so forth, without requiring any change to the specification and the underlying models. Again, this is all getting too abstract, so let's get into specifics and see what this all means in terms of the things we need to model. Let's consider platform independence in terms of a domain's internal vocabulary. If we say, for example, that an aircraft has an ID, heading, airspeed, altitude, and so forth, this is true for all platforms. These are facts about the real world. The policy that given an ID, you get a unique aircraft, is also a platform-independent fact. Now, if we say that the heading is a compass direction with a certain required precision, we're still platform-independent. And if we say that the compass direction is a rational number between 0 and 359.99, let's say, still platform-independent. But if we say that it must be a double, boom, that is platform-specific. We're now telling the programmer how to write their code, as well as making an assumption about the chosen programming language. The execution semantics described in this course allow you to express your system's vocabulary in a way that supports any choice of implementation data structures. We can specify real-world synchronization requirements as well. In our elevator example, we have a rule that the cabin cannot move until the doors have closed, and once moving, The doors cannot open until the cabin stops at its destination. To express this with execution semantics, we need to model the real-world states of a cabin and show how they must be synchronized with those of its door. And to be truly platform independent, the synchronization rules must specify the same result regardless of the implementation. So whether the implementation is single-threaded on one CPU or distributed across several should make no difference in the observed system behavior. By modeling our synchronization requirements with strict platform-independent execution rules, you'll rapidly expose all kinds of nasty edge cases. And by resolving these cases in our models, we ensure that the edge cases are anticipated across all potential implementations. But what about specifying computations? To create fully executable specifications, we need primitive actions. These specify essential computations, data access, decisions, coordination inside a domain, external interaction between domains, and so forth. Basically, they specify the things that need to be done. There are a lot of platform-independent principles involved here, and we'll get into all that in the course. But here, I'm just going to single out one principle that I think is extremely powerful. One of the places where it is easy to overspecify is to tell the programmers the order in which actions are performed. We kind of do this by accident without realizing it. There's this natural assumption that the things we need to do happen in vertical sequences, since that's an easy way for us to read and write things. Well, for us English speakers at least. The problem is that we make it difficult for the coders to determine where they can take advantage of concurrency and distribution in the code without breaking the specification. To be truly platform independent, we're going to flip the script, so to speak. To suit the nature of reactive systems, our models operate under the default assumption that everything can happen in any order or simultaneously unless a sequence is explicitly stated. Consider this pair of computations, for example. At first glance, you would compute A and then D, but you would get the same result in the opposite order, or if they were computed simultaneously, since there's no data dependency between them. In this next pair, however, the order is significant since you have to compute A before you can determine G. So implicit assumptions about the linear order of text can overspecify when it comes to actions. Though we could, I'm not arguing here that we should draw bubble diagrams instead. But if we use text, our action language syntax should, and in fact does, allow us to explicitly specify dependencies that are universally sequential with the underlying assumption that the implementation ordering of actions are entirely up to the developer. Now, math dependencies aren't that hard to solve, of course, but we'll be specifying actions that involve services and manipulate data in all kinds of ways, and it won't always be so obvious where sequence is critical and where it isn't. So we're reinforcing the theme that we give developers or code generators maximum flexibility without the danger of violating our specification. In other words, our modeling approach encourages us to provide complete computation details without specifying an implementation. Now, I'm not saying that the entire software specification should be platform independent. There will be lots of platform-specific requirements as well. I'm just arguing the benefits of identifying and modeling as many platform-independent features of your system as possible, and then managing the details separately. But why? I mean, for your project, you're probably so concerned about delivering a functional system that you don't care about supporting multiple implementations. I mean, it's a supporting use case, but there are lots of other compelling reasons to keep the platform-independent stuff separate, even if you're focused on a single deployment. Let's take a look. First off, platform-independent thinking is a powerful mental tool for tackling system complexity. Whenever you fold in the details of a given platform or implementation, you may not realize just how many factors of complexity and how much noise you bring into whatever subject matter you're trying to understand and describe. By setting these details aside, we put the focus on our essential requirements, and when we do that, all kinds of nuances that would have been hidden in the woodworks come to light. This makes it a lot easier to solve fundamental problems and make sure we haven't missed anything. Our specification of cabin door synchronization, for example, would only be complicated by folding in the mechanics of a particular programming language, operating system, or thread management system. And by reducing complexity, we increase transparency for our stakeholders and subject matter experts. It's much easier to walk an executive, manager, or an end user through a simple model of synchronization than to have them read a ball of C++ or Rust or whatever. Another reason that we keep our models platform independent is because no matter what anyone on the project might have you believe on any given day, the target platform is always subject to change. And at least one seismic disruption in the course of a project is a matter of when, not if. Technology and design decisions proceed rapidly and often for really good reasons. In fact, the specification and models should facilitate rather than hinder the adoption of improved software or hardware technology. But the essential purpose and behavior of a system isn't directly influenced by the same agents of change and is often relatively stable. Think about it. Let's say, for example, that you've modeled the required cycle of cardiac pacing intervals. Significant advances in the understanding of human heart therapy are not as likely during the lifetime of an embedded device project. And even if they do happen, they would be decoupled from platform technology changes. Decades of advances in elevator technology don't change the fact that the cabin shouldn't start moving until the doors are closed. I have tons of these examples, by the way, but I think you get the idea. So you shouldn't have to rewrite or rethink your models each time a new library, service, framework, programming idiom, or other aspect of implementation is considered. Otherwise, you have no chance of ever completing them. And that, by the way, is one of the common failing points plaguing the history of model-based software engineering. Separating out the platform from our model of essential behavior gives us a huge advantage when it comes to ensuring consistent, safe behavior across product variations. Here we have a range of devices, each providing some subset of the overall pacing behavior based on different therapeutic needs. In all of these devices, we still have to manage the same human physiology, and our core model of that physiology must be present in each. If you rethink all or part of the model for each device, there's a good chance that you'll miss edge cases here and there and reintroduce new, previously solved problems. Keep in mind that each separate team of engineers has a different mix of expertise, and will end up rethinking aspects of the behavior that were already sorted out by possibly more experienced subject matter experts. This is just one example, but good models capture essential knowledge and decisions that take a lot of effort to formalize. Once that's done, the last thing you want to do is redo the work just because you're running on different hardware or a different operating system. Benchmarking is yet another benefit of platform-independent modeling. You may want to know how your system stacks up against the competition. Your competitors are almost certainly delivering overlapping features on a different platform. If your models are platform-independent, you can use them to drive the evaluation of your competitors' products. Let's say you're delivering an autonomous vehicle and you want to compare safe intersection traversal. If you have an underlying model of intersection traversal behavior, you can use the same model to evaluate the behavior of both your and your competitor's vehicle. Not only that, you can even use it to see how you stack up to a human executing the same task. So that was a brief intro to the three big concepts that combine to help us avoid many of the common pitfalls of modeling complex software systems. Here are the key points to remember about each of these concepts. Let's start with how we manage the separation of concerns by considering the box-in-box alternative. As you know, requirements change over time. They change a lot, right? If we were to directly map features and functions into a box-in-box hierarchy, even if we're clever about it, we've built a structure based on our concept of the requirements at a given point in time. And the first batch of requirements changes is going to force us to consider restructuring. Now, if we've already built a detailed set of models based on that now questionable box structure that we started off with, we need to either refactor and do a lot of rework, or just hack what we have, which won't be pretty. Rinse and repeat for each batch of changes. At some point, you just throw up your hands and give up on your hacked model mess. So it's really important that we start off with a stable, earthquake-proof foundation for our models. It turns out that the network of subject matters required to specify our software doesn't change that much. We can lock that domain diagram down in a week or two and get going modeling vocabulary in the most important domains. And the vocabulary necessary to express a given subject matter is also unlikely to change anywhere near as frequently as the functional requirements. We can then model all our functionality and behavior on these firm foundations. So separation of concerns is about establishing a stable organization so that we can focus in detail everywhere without overspecifying the implementation. Executability establishes a bottom level of detail to ensure that we don't underspecify. We don't just draw our models, we're forced to actually get them working. This in turn forces us to check our logical consistency and ensure that we have complete coverage. And that means we'll find a lot of platform-independent edge cases we would otherwise have missed. Platform independence means we don't have to redo the models with each change in the platform technology. It also means that we can retain our focus on essential safe system behavior without being distracted by the intricacies of the platform choices. We also ensure that the same safe behavior is replicated and validated on all deployment variations. And we can use the very same models to benchmark our competition or compare against industry standards. And also, we're specifying our required system behavior without unnecessarily constraining the implementation choices of the programmers or code generators. All that said, models have a long and troubled history within the software community. In this short introduction, I can't do justice to all the things that can and probably will go wrong as you pursue a model-based approach in your organization. Here I'll chart out some of the general areas, and then we'll drill down into some of them in the course. I've identified a few, and certainly not all regions where you can expect trouble if you aren't prepared. And keep in mind that my focus is on models that specify the required software, not necessarily the totality of MBSE. The areas of concern are the quality of the models themselves, organizational obstacles, and a whole set of issues concerning the available tooling. A lot of times organizations invest heavily in tooling and tool training without investing in the acquisition and development of requirements analysis and model-based problem-solving skills. There's this prevailing attitude that if you just grab a few good programmers, you can have them draw rectangles and lines. I mean, how hard could it be? Well, I'm here to tell you that it's pretty fucking hard. Not the drawing, but knowing what to draw and why. So you end up with otherwise competent engineers poking around tool menus and drawing canvases without solving the hard problems that pave the way to quality software engineering. Many of the resulting models don't go deep enough to solve the hard problems, or you get overly detailed models that overspecify the implementation. Sometimes you get tons of abstract diagrams without any text that clearly justifies and describes the thinking behind them. I know I said in part 1 that natural language by itself is of limited value, but it's absolutely essential if you expect anyone downstream to take your work seriously. But again, that's why I'm publishing this course, to put the focus on the analysis and modeling skills required to build strong models with whatever tools you happen to be using. This leads us into organizational challenges in general, training and talent acquisition being just one of them. You still have the problem of successfully incorporating the modeling process so that it provides a seamless bridge between the stakeholders and the software engineers. Again, this is not an easy problem to solve. Somehow you need to get from requirement specification to models to the developers and then maintain that process with ongoing engagement from stakeholders, subject matter experts, and software engineers. Models need to be reviewed and improved without redoing them constantly or just giving up halfway through. The model should be driving design, simulation, validation, and testing as soon as possible. Instead, fawning over tools and tool-specific training tends to soak up most of the attention and budget, even though this is really the least of your worries. I've observed that there are often unrealistic expectations in the early stages of what MBSE is supposed to accomplish. This then leads to a lot of uninformed decisions that pave the way to eventual failure. The tooling you use for model development and maintenance can help and hurt in a lot of ways. I like to compare the look, feel, and productivity of a modeling environment with that of a modern IDE for software development. Unfortunately, model development environments rarely, if ever, measure up to their code development counterparts. In particular, there's a lot of unnecessary tedium associated with pushing pixels around to create, maintain, and organize diagrams. Configuration management for diagrams is also problematic. If it is even possible to diff two versions of a model, can you distinguish between cosmetic adjustments to layout versus a change in the underlying semantics, such as a change to an attribute, event response, or computation? The biggest challenge is what a colleague of mine refers to as tool infatuation, where modelers become focused on the needs and mechanics of the tool rather than the most effective modeling solution. Your goals should drive tool usage, not the other way around. If you don't have a clear concept of your goals, then the tooling becomes your master, and that's just not a path to success. I say this because I've seen way too many team members filling out documentation forms, clicking boxes, pushing pixels around as kind of busy work just to complete a required artifact without any clear sense of connection between it and what actually impacts the software development and validation process. And don't even get me started about team members not being able to access models because there's always some license issue. Arg. That said, should you just bail on the whole MBSE thing? There are certain kinds of systems where I might recommend just that. But assuming that you're building large, complex, safety-critical systems, I would argue that you're far better off tackling the MBSE challenges. But you need to know what you're getting into. Your alternative is to write sloppy specifications, end up with poorly planned software architecture, have difficulty validating your system, and struggling with unsafe software. And that's no party either. There are solutions to all the problems I've mentioned, but you have to anticipate them, have a plan, and devote the necessary resources. I certainly don't have all the answers for your particular organization, and you shouldn't trust anyone who claims that they do. But I do have substantial hands-on experience working with numerous organizations with both successes and failures under my belt, and I'm happy to share my stories in this course to help you out as best I can. This course is not specific to any particular standards or tools. That said, you should be able to apply the concepts in part or whole with whatever standards and tools your project happens to be using. As long as you have some way of entering text, tables, drawing or generating drawings of state machines, class diagrams, and some sort of hierarchical diagram composition, such as they do with SysML, for example, you're good to go. You may need to be resourceful and cobble together artifacts outside of your tool framework using spreadsheets, text files, and so forth. I always emphasize that the tools and standards should be working for you and not the other way around. Solve the engineering first and cast the solution with the standards and tools second. So here's the plan. I'll be dropping new videos on my YouTube channel on a bi-weekly basis with the intention of delivering a more or less complete course by the end of 2024. I'll announce the new videos on LinkedIn and other social media. And if you don't want to wait that long, feel free to contact me to explore options. Also, I'll keep comments open and do my best to respond.